Hello and welcome back. In this tutorial, we're going to be looking at physics homework number 3. PH number 3 centers on graphical analysis of a displacement versus time graph. Sometimes you'll see it as displacement versus time, sometimes you'll see it as position versus time, and every once in a while you'll see it as distance versus time. Basically, this is a graph of how far you went and how long it took you to get there. What we're also going to be looking at is the concept of a best fit line, the slope of the best fit line, what the units of the slope represent, what the physical quantity of the slope represents, and being able to come up with an equation to predict where the object would be at any point. Let's begin. Please remember to pause or rewind the video as needed. Number 1. On the graph above, use a straight edge to draw a best fit line. Well, if you open this up using the Kami app, then you want to select the shapes option over on the far left and then insert line. What we're going to do is we're going to go ahead and draw a line that basically plows right through the middle of the data points. Something like that. And what you can see is you can see that there are some points above the line, like that, kind of that. You can also see that there are some points below the line, okay? But it's fairly balanced. We could even go so far as to take this and kind of scoot it down a little bit like that. Okay, there's our best fit line. Now, in part 2, we're going to calculate the slope of this best fit line. Okay, now I'm going to be doing a lot of work on the graph itself, and then we'll represent our answers over to the side here as we go. Okay, so to find the slope of the line, not the slope between data points, but the slope of the line. To do that, I'm going to find 2 points where the line intersects the corner of the graph paper, like this point here. This point here intersects that box right at that location. So you find 2 of those and you circle them. Keep going up the line until you find another. There's another point right there. Now we're going to draw a slope triangle that goes from one of these points to the other. Okay, now the first thing we need to do before we start counting boxes and figure out rise over run, figure out what your scale is. Figure out what each box represents. Okay, so to figure that out, I can take 0.2 and 0 and subtract them. So if I go 0.2 minus 0, I get 0.2, and divide it by 5 boxes. There's 1, 2, 3, 4, 5 boxes in between. So that means every box is 0.04, right? That would be 0.08. That would be 0.12. That would be 0.16, and so on. Every box is 0.04. Okay, now on the x-axis, which is the time axis, you can see every box is, I take the number 0.25 and 0, subtract them, I get 0.25. Divide that by 1, 2, 3, 4, 5 boxes, and you can see that each box would be 0.05, 0.1, 0.15, 0.2, 0.25, 0.3, 0.35, 0.4, 0.45, 0.5, and so on. So each box is 0.05. Okay, each box on the y-axis is 0.04, each box on the x-axis is 0.05. Now what we can do is we can calculate our rise and run the following way. You can see it's 1, 2, 3, 4, 5, 6, 7 boxes going up. So I'm going to go 7 times each box. So 7 times 0.04 gives me 0.28 is my rise. 0.28 meters specifically. Write down the unit so you can keep track of that and give your slope physical meaning. Same thing on the x-axis, or the run. So we're 1, 2, 3, 4, 5, 6, 7, 8 boxes times each box being 0.05. So 8 times 0.05 is 0.4. 0.4 seconds, because the run is time and time is in seconds. Okay, and there's our slope. Okay, well, those are the rise and runs of our slope. So the slope, I'll do this over here. The slope is going to be So rise over run. So the rise would be 0.28 meters over 0.4 seconds. Go ahead and divide those. 0.28 over 0.4, and we get roughly about 0.70 meters per second. Okay, so our slope for part 2, our slope is roughly about 0.70. Okay, now the units for this slope, okay, meters per second. Okay, we'll talk about reasonable error in just a minute and how to do that for part 4. What physical quantity does this slope represent? Well, meters per second is the unit of velocity. So the slope represents the speed or the velocity, okay, of this. Now, let's figure out the max and min slopes so we can figure out what is called estimated error of a slope. All right, now here's how we do that. We're going to basically kind of go from low point to high point and high point to low point to get max and min slopes. I'm going to use different colors to represent that. My max slope, which I'm going to do in blue, is going to go more or less from this data point, which is pretty low, to about that data point over there, which is pretty high. Okay, so it's going to look kind of like this. Okay, there's my max slope. Okay, now let's go ahead and find the max slope. Same idea, same way we go about it. So I like that intersection point there. Could even make an argument for that one right there. So my max slope, I'm going up 2 boxes. 2 boxes times 0.04 gives me a rise. So there's my rise, there's my run. I have a rise of 0.08. My run is 2 boxes. 2 boxes times 0.05 would be 0.1. And if I go 0.08 divided by 0.1, I get 0.8. So my min slope is 0.08 over 0.1, which is 0.8 meters per second. This is my, I said min slope, didn't I? I'm sorry. Max slope. This is my max slope. You can see how the blue line is steeper than the black one, which means that's the maximum possible slope based on these data points. Now the min slope, same concept. I'm going to go from, I'm going to use a different color here. Let me do gray, I guess. So I'm going to go from kind of a higher data point to kind of a lower data point on this side, right? So same idea, other way. A little tricky at first getting this drawing done. Okay, something like that. Okay, now, let's see, I like that point there. And I guess we can go to that point right there. So you can see I have 4 rise boxes. So 4 times 0.04 gives me a rise of 0.16 in a run. 1, 2, 3, 4, 5 boxes times 0.05 is 0.25. And my min slope would be 0.16 meters over 0.25 seconds. 0.16 over 0.25, and I get about 0.64 meters per second. So those are my best fit slope, which is basically my average velocity. It's the average of your data points, but a graphical average. My max slope, based on the maximum possible error, and my min slope, based on the minimum possible error. Now, your estimated error is basically half the difference of those two. So take the difference of those two. We're going to go 0.8 minus 0.64, okay, and you're about 0.16. Take half of that, right, and we're looking at about 0.08. So we're looking at plus or minus 0.08 meters per second. Okay, now determine an equation of this line using y equals mx plus b. So let's fill this out. On the y-axis, we have displacement, which is going to be x. Technically, it's delta x. Okay, technically, it's delta x. So what I'm going to do, though, is I'm going to write it as position rather than displacement. So we're going to go ahead and write it as x. So x equals, now m is your slope. Our slope is 0.7. So in parentheses, I'm going to put 0.7. Then I'm going to put plus or minus my estimated relative error, 0.08 meters per second. Okay, and then plus b, well, that represents your y-intercept, right? So what's the approximate y-intercept of my best fit line? You can see it's running right into almost 0.08. Okay, now test your equation by using it to predict the displacement of the object at 0.4 seconds. So you're just going to take 0.4 and plug it in right. Oh, I forgot. I'm so sorry. I forgot the t. So it's velocity times time plus 0.08. So we're going to plug that 0.4 seconds in for time. So if I go, now keep in mind, I'm using my average, which is 0.7. So 0.7 times 0.4, okay, and then add 0.08, I'm roughly at about a position of 0.36 meters. And if you go on the graph, you can kind of verify that. You see 0.4 would be about right there. And if I go up to the graph, which would be the black line, and then go over, right, it's, whoopsie, it's kind of right about there. And that's 0.36 right there on the graph, right there. Okay, we're not going to do part 8, so go ahead and strike a line through part 8. We're not going to make a bar graph for suggesting that, but basically it's comparing our prediction with the plotted displacement at 0.4. The plotted displacement at 0.4 is exactly at 0.36, and so you'd have a comparison of essentially zero difference. We're going to do 10, 11, and 12 kind of down below where you have room. So, or 9, 10, 11, excuse me. 9, okay, is asking us to write a sentence conclusion regarding the ability of the equation to predict the displacement of the object. So basically the equation predicts any position given a specific time, right? Its position as a function of time. Now, from your graph, determine the average velocity. Well, the average velocity, right, is the slope of the best fit line, which in this case would be my 0.70 meters per second. Now, in the case of number 11, it says determine the average acceleration. Well, average acceleration, guys, is your change in velocity over time. But this is modeling constant velocity, so there really is no change in velocity over a 1.25 second time interval, which means we have really no acceleration. Okay, I hope you found this tutorial to be helpful. See you next time.